In this figure, we have two surfaces. We have this blue surface right here, given by y equals x squared plus 3z squared plus 1. And then we have this tan surface right here, given by y equals 5 minus 3x squared minus z squared. And it might be worth it if you want to go to a 3D graphing utility and put these in so you can manipulate it and move it around and look at it. But it does have some symmetry around the y-axis here. So we want to find the volume contained between these two surfaces, in the intersection of these two surfaces here, which is given by this kind of curvy line right here. All right. So the first thing to think about is basically what you want to integrate with respect to first. What's your inner integral going to be? And so for me, I think about these kind of pillars here. I want my pillars that I could divide this region, this surface, actually volume might be a better word, up into. I want it to touch one of these surfaces, the bottom of that pillar, and then I want the top of that pillar to touch another one of these surfaces up here. So I want to go this way. Notice if I did my pillars up and down, I'd have to split this into a lot of different integrals, maybe at least two, I don't know. If I did my pillars in the z direction, it'd be touching the tan surface here, then here it'd be the blue surface to the blue surface, and then I'd have to figure out the region I was integrating over by projecting this down into the xy plane. I don't know. I think that seems very, very complicated. But if I do my pillars this way, then I can think about this intersection here projected this way into the to the zx plane, and this will give me the region in the zx plane that I will integrate over to add up all these pillars. Okay, so let's start off with thinking about the length of one of these pillars. Now, this y value here is greater than this y value. So to find the length of this pillar here, I'm going to take 5 minus 3x squared minus z squared and subtract x squared minus 3z squared plus 1. So let's go ahead and take a look at that. All right, so if we do 5 minus 3x squared minus z squared subtract x squared plus 3z squared plus 1, we are going to get, let's see, 5 minus 1 is 4. Then we'll get negative 4x squared. And for our z's, let's see, we're going to get negative 4z squared. So this is we could think of this as some function of x and z. And now we want to add up all of these values over this region here. So we need to figure out what our bounds are going to be over this region. So this region is obtained by finding the intersection curve of these two graphs. So to find that, we are going to set these equal to each other. All right, so when is the y value of the tan curve equal to the y value of the blue curve? Well, let's see. Let's just get our variables on one side and our constants on the other. Let's move the constants over here to keep things positive, and so then we'll have, let's see, what do we have? 4x squared and 4z squared. That's pretty nice. So if we divide everything by 4, we get 1 equals x squared plus z squared. So what is that? Well, that's a circle in the xz plane with a radius of 1. Right, so this is a radius of 1, radius of 1. So here's a picture looking straight on to the xz plane here. All right, so let's think about how we're going to set up our integral. So now we know we need to integrate over this area, this region in the xz plane. And we are going to have our function of x and z in here. which is 4 minus 4x squared minus 4z squared. So now we just need to decide whether we're going to do dz dx or dx dz. And actually, we could make another decision here. We could do r dr d theta. You want to change it to polar? We could do that. Let's think about that for a minute. No, let's think about all these. All right? Let's actually think about all of these. Let me make these different colors here. And let's think about that. All right, so for option 1 here, if we wanted to do dz dx, so that would mean we're going to fix some x. So we would fix some x like that. And then we would let our z's go from the top of the circle to the bottom of the circle. So here's our equation right here. All right, so if we solve that for z, we would get the positive square root of 1 minus x squared and then the negative square root of 1 minus x squared. So our bounds would have to be those things there. Okay, we'd have to do this for our bounds. And then our x's would, our pillars here, are not pillars, let's call these line segments, would range from -1 over to 1 for our x's. Okay, so that's that option. All right, so keep that in mind. I'm going to erase those and we're going to do it the other way. Okay, what if we do the other way and we do, let's do dx dz. Well, that's going to be kind of similar, isn't it? So we're going to, in this case here, we would fix some z value. So we get these segments going this direction. So x is going to range, let's see, what does x equal here? If I solve that for x, I get negative square root of 1 minus z squared, positive square root of 1 minus z squared. So we would do that. Pretty similar computation, right? It's going to be very similar, but a little bit messy probably. And then my z's are going to range down here from -1 to +1. Very similar. Okay, so either one of those, if you decide to go that direction, I don't think it makes that big of a difference. Now, what if we do polar? Is that possible? Well, I mean, the bounds for polar are pretty darn nice, right? I mean, we've got, splitting these up here, these radii are all 1. So a maximum of 1. They're going from 0 to 1. Those would be your bounds for your r. All right, so r dr d theta. So r is going to go from 0 to 1. And then theta, you know, that's just going all the way around the circle here. So that's just going to go 0 to 2 pi. Those bounds are pretty darn nice. No variables at all. But now I'd have to change that into polar. All right, is that tough to do? No, it's not. All right. So we have 4 minus 4x squared minus z squared, or 4z squared. So let's take a -4 out of those last two terms, and we get that. So now if we're looking in the xz plane, what is x squared plus z squared? It's similar to x squared plus y squared in the xy plane, right? So if you have some point here in the xz plane, the coordinates of this is xz, just in the xz plane. So x squared plus z squared equals r squared. So I could just change this to 4 minus 4r squared. I kind of like that. Now you could, as an exercise, go through it in all these different ways and you should get the same answer. But I'm partial to using polar here because my bounds are not going to have any variables in it, and my integration looks pretty nice, although this integration with the x squareds and z squareds isn't too bad either. So remember to put your extra factor of r in there. Alright, so I'm going to encourage you to pause the video and complete this integral and then restart it and check your answer. Alright, how'd you do here? So you may have done this a different way, but you should have got 2 pi. I just took this guy out. This inner integral is not dependent on theta, so I separated it out as a constant times that. And Alright, I want to say a couple things here about this. Now, this is actually an example from your book, and the way that they approached this, again, was using a triple integral. We talked a little bit about this in the last video. And so this inner integral here is basically finding what this length is, like integrating with respect to y, and the y value ranges from the y value on the blue surface to the y value on the tan surface. If you do this integral right here, if you do this inner integral, you're just going to get 4 minus 4x squared minus 4z squared. So for me, it's just easier to do this minus this, okay? And not do a triple integral. Now let me say, you can only do this when we're finding volume, okay? You can only do what I'm doing here if basically when you're finding volume, the function here, notice there's no function. This would just be like 1 dy. We've done some density problems, you know, where maybe each one of these points in here is assigned some density function. I think we did one yesterday that was 1 plus xyz. Okay, so if each of these points has some different density and we want to find the total mass over this whole thing, then you're going to have to do 3 integrals. You can't just do this minus, you can't just do the length of this pillar, because now every point on this pillar is assigned some different density. And you do have to do the integral to add up all the densities in each pillar. Okay, so you can only sort of cut to the chase and subtract these two guys like I did here and avoid 3 integrals if you're just strictly doing volume and there's no other value assigned to each of the points in your solid.